Morning. Shall we get started? Hi. Yeah, so I think everybody has seen that I've delayed the homework, the programming assignment to today, and then the deadline is Wednesday. Originally it was Friday, I think. And we will have an exam next Wednesday, and it will be on homework 4 and 5. So, like communication primitive, sorting, dense matrix algebra. That's pretty much it. There will be no MPI on it, so it will be everything like up to the last lecture, minus the bit at the end about MPI. And not including what was on the first exam. Everybody good? Any questions? Yes. I will post them today. Yes. Yeah. So yeah, that's pretty much it. And programming assignment 3 is going out today. I think it should already be out, but you can look at it later today. Yeah, it's actually, I think it's pretty fun. It's doing sparse matrix multiplication and a couple of applications for that. Yeah, take a look at it early. I would say it's comparatively difficult to the second one. I don't know. It's a matter of opinion. Like it's more algorithms based rather than like programming assignment 2 is about implementing the primitives, and programming assignment 3 is like you use the primitives to implement an actual algorithm. So it depends on your opinion. But yeah, so we'll just continue with MPI from last time. If you remember, last time we were doing like Cartesian coordinates and MPI, and there's just a couple questions from last time that I looked up. So one was, does making a new communicator overwrite the old one? The short answer is no, and the longer answer is no, but technically the documentation recommends that you duplicate MPI ComWorld. Like technically they recommend that you never directly use MPI ComWorld, because if you have multiple libraries using it, you might have issues. But in our purposes, like we only have one thing going on, so it doesn't really matter that much. And another question was, when you do com split, can ranks be the same? Like if you remember, like there's color and key. And as long as things within the same color are different, they can be the same across colors. Okay, so just to recap from last time, the Cartesian in MPI you can define Cartesian topologies, which are just n-dimensional topologies, and these are just in some sense they're like convenience functions, because of course like you have your ranks 0 through ranks -1, and you could just logically arrange them in a grid with whatever dimensionality you want using like index calculation, but it's a bit complicated to do that. So this is just something nice that they provide you, which is cart rank, which gives you a rank, give it a Cartesian location, and then the reverse, which is given a rank and number of dimensions and a communicator, which is already arranged in a Cartesian topology, give a tuple of coordinates of D, where D is the number of dimensions you have. And then this is just recap from last time. There's also this functionality where often a thing that you want to do is you have a 2D grid or any grid, and you want to shift along some axis in your grid, just like by 1 or by some arbitrary displacement. So they give you this functionality, which is you pass in a communicator, a dimension that you want to shift along, displacement, which is how many you're shifting along, like 1, like usually it's 1, if you kind of shift to your neighbor. And then this is the output, which is it gives you a source rank, which is the rank that's sending to you, and a destination rank that you are sending out of. So like if you remember Cannon's algorithm that we did last time, a common thing is you want to shift, we shifted like left and then we shifted up. So to get that, you would put the dimension, if 1 is like horizontal, then 1 would be displacement 1, and then up would be displacement 1 in the other dimension. And that would get your neighbors. And note that this is not actually doing the data transfer, it's just giving you the index of the destination resource. Okay, so this is an example of how you would use it. Suppose we have 2 dimensions. In the beginning, we need to figure out the length of the dimensions. So we put in the size, which is how many ranks we have. We put in 2, which is the number of dimensions we have, and then we put in this pointer to the array. And MPI is going to fill the array with the dimension lengths, so you don't have to decide that yourself. And you have to pass in whether or not the dimensions are periodic, which means that if this is false, then they are arrays. If this is true, then they're rings in that dimension. And then you pass in the communicate. Then you're going to create a new communicator. You create the Cartesian communicator, 2 dimensions. You pass in the dimension lengths that we got, the periods, whether or not we can reorder the ranks, and then we get out a new communicator. So this would give us a true 2D array, not like a torus. And then if we want to get our neighbors, we have down, up, left, right, and then we need a space to hold the neighbors. And then to get those, we pass in, like we're using this cart shift function that I just talked about, and we pass in the new communicator, which is in a Cartesian topology. Dimension is 0, displacement is 1, and then that would give us as a source the left and as the destination the right. And for dimension 1, then the source is down and the destination is up. And because this is an array, sometimes, like if you're at the edges, then the next is the source or the dest may not necessarily be defined, so it would pass you in like a random number or a negative number. So that would mean that there is no source or destination, depending on where you are. Any questions so far? All good? Yes.
So when it's an array, does that just mean like if you're on the edge, like you just can't like send the one that's round, or you can send anything?
You could send to anything. It would just not be defined as your neighbor in this. Like you could directly send point to point. Yeah, good question. We'll do an example where I'll show how you would get the negatives. So if you remember way back when we were talking about MPI first, there's this functionality called send receive, which is basically send and receive at the same time. The API is sort of like if you concatenate the APIs for MPI send and MPI receive. So you have a send buffer, how many you're going to send, what is the type, the recipient, which is the rank, the tag, and then that's kind of like the end of the send API. And then the rest is the receive API, which is the receive buffer, how many you're going to get, what type you're going to get, who's sending it to you, and a tag. And then this is just the communicator status. So that's like extra metadata. And this is just a combination of send and receive. And the reason that I'm bringing this up is because I'm going to use it in an example with the Cartesian coordinates. Okay, so this is just an example of how you would use it. It's just like if suppose that there's just 2 processes. So first we fill this int, which is some buffer. If your rank is 0, then you have 1, 2, 3, 4, 5. Otherwise, you have 7, 6, 8, 9, 0. And then in send receive, you send. Here is just your neighbor, like 1 if you're 0, and 0 if you're 1, just the other one. And then so you send the buffer 1, you send to your neighbor, and then you receive 1 item into your receive buffer. And then the beginning receive buffer is empty. So in this example, P0 would send P0 sends what it has and receives from the other one. So it sends 1, 2, 3, 4, 5, and it gets 6, 7, 8, 9, 0, and then vice versa for P1. And again, notice that receive buffer and send buffer, they have to be different because it's not defined if they're the same. Okay, so this is a more complicated example, actually using the Cartesian coordinates. So let's go through this. The dimensions, let's say we have 2 dimensions, 0, 0 in the beginning, and period is 1, 0. So it is a ring around dimension 0, like let's just say that's horizontal, and dimension 1 is like an array. And we have coordinates, which is everybody has a 2-tuple of coordinates based on the dimensions that are defined. And this is just initialization, like get my rank in the world, get the total size, and based on the size, we create the total dimensionality in the entire 2D grid. So for dims create, you pass in size, you pass in the number of dimensions that are happening, and dims gets filled out with the length of each dimension. And this is just printing, like if I'm the rank 0, then you print, like you turn up my dimensions. Or if I'm the rank 0, then you print the dimensions of the entire 2D grid. And then you create a communicator using the things that we got. So the length of the dimensions and the period. So this is making the 2D grid. You can get the rank within the new communicator from here. And then the coordinates are just like a two tuple. The source, and then we used cart shift to get the source and the destination. So this is exactly the same as we just used it. Like this is dimension 0 and displacement 1, so it's left and right. And then this is dimension 1 and displacement 1, so that's source is down, destination is up. And left and right are always going to be defined because this is a ring, but up and down may not necessarily be defined because it's an array in the vertical dimension. And then this for loop is going over the dimensions, and then it says for we buffer in as 0 first, and then we set out as our C rank, which is the Cartesian rank. And then while for every step of the length of the dimension, we're going to do the send and receive. So we receive what our in neighbor is getting us into in, and then we send what is in out over here. And we add to some running total in the sum. And then we just pass like we set out into in. And at the end, we print everybody's, this is the world rank, this is Cartesian rank, this is the sum that we got, or the source, the destination, and the sum that we got in dimension 0 and dimension 1. And that's the end. So what is this actually doing? Well, we can look at an example. So suppose our grid is 4 in this dimension and then 3 in this dimension. And again, this is a ring in the horizontal dimension, but an array in the up dimension. So just ignore the sum for a second, and then we can look at the ranks. So world rank, this is like nicely ordered for convenience, 0 through 11. We have 12 ranks, and the Cartesian ranks, the total ranks are actually the same as the world ranks, like 0 through 11. But when we print the pairs, we get like 0, 0, 0, 1, 0, 2, and so on. So these are, like I said, there's two tuples. And along dimension 0, looking at this one, 0, 0, the source is rank 9, which is this one, and the destination is rank 3, which is that one. So, like I said, right is disk, left is source, and then it wraps around. So again, similarly, like for 3, which is this one, the source is 0, which is here, and then the destination is 6, which is that one. And then if you look at the vertical ones, then it gets a little weird. For dimension 0 for 0, 0, source is negative 2, because like there's no up. This is passing downwards, so there's no up neighbor for this one, and then destination is 1 in that direction. Any sense? Yes. Yes, because we passed in MPI com world to begin with. So if we look here, good question. So yeah, in cart create, we passed in MPI com world. So it would create a communicator from all of these things. Yeah. Mm-hmm.
What does shift do? I thought shift.
Oh yeah, shift is just you pass in the communicator, you pass in a dimension that you're going along, and a displacement, which is how many steps, and then it will fill out source and dest, which are just like what you would get from and what you would send in this dimension and displacement. What source and dest are ranks.
So the shift is 1, like it has a displacement of 1 line, so like offset by 2.
Why is it offset by 2?
Like for example, like 9 sends stuff to 3 offset.
9 sends stuff.
Yeah, 9 does it.
9 along dimension 0, the source is 6 and the dest is 0, and then along dimension 1, the source is negative 2 and the dest is 10 or 9. So it would be like nothing is here and then dest is here.
Oh,
and then that one. Yeah.
is 9 always
I think it probably depends on the implementation of MPI, but it would be something negative.
But does the actual negative number mean anything, or is it
No.
just the fact it's negative?
I think it's just the fact that it's negative.
Does that limit
You can still call like MPI send, for example, point to point between arbitrary ranks. Yeah, this is just like you're not limited to what was in the shift. This is just it's like a convenience function because often in algorithms you do the shifting, but like if you did need to, like you could call like MPI send from 11 to 0, and that would still be valid. Yeah. And for there, you would just use you just use the Cartesian rank here, which happens to be the same as the world rank in this example, but not necessarily always. So you would get that from in there, it's not here, but there's a function like MPA cart rank, and then from there you can get the Cartesian. C rank actually is here. Yeah, you get the com rank. So you just get the rank in your new communicator, which is the thing that got created here. Yeah. So okay, so we set up the neighbors like left and right, up and down, and now we have to compute the sum. So if you remember, sum started as in starts at 0, and then out starts as the C rank, which is the world rank. And at each step, we're going to add what we got into the sum. So if we just look at 0, 0, the sum here ended up being 18 because we are adding up the world rank, which happens to be the Cartesian rank in every one of these things. So we're adding up 3, 6, and 9. And then the same for everything in this row. So if you look at 1, 0 as well, the sum is going to be 18 because we started here, but we're still passing around like these 4 elements, 3, 6, and 9, and we just add them into the running sum. And then the same for the different rows. So like for 0, 1, we would get 22, which is these numbers added up. 1, 4, 1, 4, 7 is 12, and then plus 10 is 22. And then similar for the third row is 26. And when we look at the columns, then it gets a little weird because there's no, let's just look at 0, 0. Like there's no source for 0, 0 in the vertical dimension. So the sum is always 0. And then the sum for 0, 1 happens to be 0 because even though we did get the rank from this one, it was 0. So we just added 0 into it. And the sum for this one is 1 because we got this rank from here. But the reason that these, like the sums in the columns don't all line up because it's for illustration, like there's no period in the vertical dimension. And then same for, like, let's just look at column 1. So the sum is, so like for 1, 0, yeah, it's 0 because there's no source again. For this one, it's 3 because we got 3 from this source. But we did 2 steps. We always do 3 steps of passing in the vertical dimension because this for loop goes over the length of the dimension. But like whether or not we get anything depends on whether or not we had a valid source, or also how many like iterations of valid source we got as well. Does that make sense? Yeah. So that is Cartesian topologies, and MPI also provides some functionality for describing graph-like topologies. So like we did some graph-like algorithms or logically graph-like algorithms. So you can actually map that onto your MPI for ease of programming. So basically you can represent this as a set of, the easiest way to think about it is that each processor is a node in your graph, and you can specify like the out and in edges. Yeah. So there's a little sidebar into graph formats because we have to think about how we're going to logically specify what the graphs look like. Yeah, so let's just think of a graph, like this example graph here. And the easiest way that we have ever learned to store the graph is in something called the adjacency matrix, which is just you have n vertices and it's an n by n matrix, and you put a 1 if you have an edge, and you put a 0 if you don't have an edge. And for symmetric matrices, it's reflected across the diagonal. And if you have a weighted graph, then these would just be weights rather than 1. But because this is unweighted, 1 is for convenience. So like here, 1 goes to 3. 1, oh, I guess it starts at 1. So 1 goes to 3 here, and also here. So you can see like this is symmetric. However, this takes space n squared, which is not ideal because in your topology, like you don't have close to n squared number of edges. So we need to come up with more efficient formats. Oh yeah, and in directed graphs, it's just, if it's unweighted and directed, then it's just binary, but it's no longer symmetric. So here, like, if 1 goes to 3, 1 goes to 3 here, but there's no 1 to 3 here. Yeah, and like I said, weighted, you just change the weights. So in reality, this goes beyond topologies. This is just for sparse matrices, as you will see in the homework, but I guess it's good that we're going to do this. So another common representation for sparse graphs, and by sparse, I mean you have just much less than n squared edges, where n is the number of vertices. Then we have a format called adjacency list, which is rather than storing the adjacency matrix, which always takes n squared space no matter how many edges you have, we store a compact version where you explicitly write down the neighbors of every vertex. So for vertex 1, the neighbors are 3 and 4, so we just write 3 and 4 here. And for vertex 2, the neighbor is 3, so we'd write 3 over there. And 3 is 2 and 6, and so on like that. And this sparse representation of adjacency list takes space proportional to m, which is the number of edges there are, and n, which is the number of vertices there are. Because if you imagine, like, the easiest way to implement this was you have like a vector of length n, and then each one points to like another vector of length degree of m, or degree of vertex u, where u is like the index. So this, the main difference between, like, I guess philosophically, the main difference between sparse and dense representations is for dense representations, it's sort of like the edges are implicit in the representation, where you don't ever actually write the vertices, you just get them implicitly through the index. And here you actually write like the neighbor is 3 and the neighbor is 4. Yeah. So that's the main difference. And the reason that I'm talking about these is because we can use those to represent the graph topologies as well as arbitrary sparse graphs. So that is adjacency list. And in reality, probably the most common sparse representation for static graphs or matrices is called compressed sparse row, which is, in some sense, it's like if you concatenated all these edge lists in the adjacency list together into one array. So like here, this is like the edges. So it's like 3, 4, which is this. Like 3, 4, 3, 4, 3, 3, 2, 6, 2, 6, and so on like that. So you put all the neighbor lists concatenated one after the other, and then now you need an array to tell you where everything is starting. So for vertex 1, you start at index 1, and then for vertex 2, you start at index 3. So these are the neighbors. And then vertex 3, you start at index 4. So if you subtract like 2 neighboring indices, then you get the degree of that vertex. Yeah. And you can generate, like if you think about how to generate this, if you had an adjacency list, if you know the degree of everybody, you can just write that into this index array, and then you do a prefix sum on it, and that's how you get the starting indices. And with this edges, like after you do this, you know the starting position of everybody, so you just write them directly in. So you just copy into here.
This is like when you have to never
change. Yes. Yeah.
That it's in like this portion of the memory.
Exactly. Yeah. Good point. So the reason that this is good is because it's often when you actually, it doesn't matter so much for defining the topologies, but in general, like if you want to implement efficient matrix or graph algorithms, often you need to traverse through like the neighbors, and this is the fastest way that you can traverse through the neighbors. But as you know, it does not work if your graph or matrix is changing, and that is like an active area of study. So, that I work on a lot actually. So it's pretty fun. At least I think it's fun. I think data structures are fun, but yeah. But this is compressed sparse row, and this is like a canonical sparse matrix graph format. Oh, sorry. Any questions on this part? Okay. Another representation, another common one that often comes in when you read in the files. Like, so this is like kind of getting into the weeds of when you do sparse matrix algorithms, but the first step is that you have to read in the sparse matrix that you're going to work on. And one common way that people write the files for sparse matrices is in something called coordinate, which is just a bunch of tuples where you write the source, test, and weight. And then that's just your entire file is lines like this. And you read it in from your file, like from a programming perspective, you read it in, you fill in like a vector of tuples, then you can convert between these formats however you like. So you can convert this straightforwardly kind of into compressed sparse row using the same idea that we talked about. You figure out the degree. You just count the occurrences of every source, which is how you figure out the degree. And then once you figure out the degree, you just create the index and you create edges. Yeah. And then this one, it uses, I guess if a benefit of this is that it always uses space proportional to the number of edges, because you just write one tuple per edge, whereas in adjacency list you had to store like the vector, even if there are no neighbors for one thing, you still have to store like the entry in the vector. So if for some reason the number of edges that you have is much less than the number of nodes, then you may prefer this format. This one is a bit logically easier to work with. It's just like tuples. So. And basically what it comes down to is all these sparse formats, you, like I said, you directly just write the neighbors, and it's basically like storing tuples, and you just want to figure out efficient ways to store tuples so that you can traverse through them, and also more advanced is that you want to like make updates, like you want to update the weight, or maybe you want to add a new edge, which is not, I guess like if it's not necessarily sorted here, you could just add the tuple to the end if you can somehow efficiently figure out that it's not already there. So that might be pretty fast. But this one definitely, like if you wanted to add anything, it would be you have to shift stuff around. So the reason that I brought all that up is because we want to use similar. We're going to use similar formats. MPI takes in similar formats when you define graph topologies. So this is MPI graph create, and then you take in an old communicator. You take in a number of nodes. Take in pointers. This is just CSR basically. Like you take in the index array and you take in the edges array, and you take in whether or not you can reorder the ranks, and you get out a new communicator following this graph topology that you just defined. Yeah. So if we look at this, suppose that we wanted to represent this graph using the MPI ranks, so 0, 1, 2, 3, 4, 5, 6. There are 7 nodes. The index is the starting position. And we always start at 0, so you don't need to write 0 in this example. So the neighbors of 0 are 1 and 2, so you write 1 and 2 here. The next one starts here. And then the neighbors of 1 are 0, 3, and 4. So 0, 3, and 4. The neighbors of 2 are 0, 5, and 6. So that's 0, 5, and 6. And then similarly, like neighbor of 3 is 1, neighbor of 4 is 1, neighbor of 5 is 2, neighbor of 6 is 2. So that's 1, 1, 2, 2. And the way that we know where everything starts is the index array. Yes. If 0 didn't have any neighbors, this index would be 0. If something has no neighbors, then like the neighboring indices are the same. Or the so like for example, let's say 1. If 1 had no neighbors, this would be like 2, 2, because the distance between these two is like the start and the end of that vertices edges in the edges array.
But so then, like, would it not just appear as if, like, if they were both 2, then would it not just appear that, like, 1 and 2 both, like, had neighbors 0 and 3?
Sorry, can you say?
So would it not just appear that both 1 and 2 had neighbors 0 and 3? If that were if, like, 1 and 2 were both point 2, like index 2 in the edges array?
Would 1 and 2 both be neighbors of 3?
That's what it would look
It
like,
would
right?
kind of look like, it would kind of look like 1. Yeah,
No, because you don't. Like think about how you would traverse this thing. Like you would have an outer loop through the indices, and then you have an inner loop where the inner loop, like start and end, are defined by index of vertex and index of vertex plus 1, and then your inner loop would just range over those things. And if those would be the same thing, then you would just never you would never enter the inner loop. Does that make sense? Yeah. So yeah, it's a good point. So it's not on the slides, but if you just think about how you traverse them, like the easiest way is with 2 loops. One is like, let's say you just wanted to read out all the edges. You would first do an outer loop over n, going up 0 up to n. So that would be your source vertex. And the way that you get the destination vertices is that you would do like, so that would be like I 0 up to n, and then the inner one j from index of I up to index of I plus 1. And then you would index into edges to get the destination, and then you could print like source and dest. Cool. So yeah, this is an example. This is an example of like how you create a hypercube using this graph create. So in like you get the size. You need the number of bits because we're gonna have to figure out the neighbors using the number of bits. And these are just this is how you fill out the edges array through the number of nodes. You go through the number of nodes, and each node is going to have k neighbors, where k is like log 2 of the total number of ranks you have. And you get the neighbors by just flipping one of the bits. Because in a hypercube, all your neighbors are 1 bit different from you. And that's how you fill out the edges array. And the index array here is simple. Everybody has the same number of neighbors. So it's just like you just add k every time. Then you use that to create, you just pass that in. So you pass a number of nodes, you pass in the index array, edges array, and you get out a new communicator. And this would be the hypercube topology. Does that make sense? So that's like how you can, that's kind of like a centralized way to create your graph topologies. Like if you notice that we passed in the entire graph topology as the argument. But you can also pass in, there's like a distributed version to do it too. So, oh yeah, okay. So this is like what we've been doing. Vertices are the processes, edges are the important connections. And there's some functionality, I've never actually used this, but it might help, which is you can pass in weights as well, and the weights can kind of tell you, like, if you know something about your algorithm that these vertices are going to communicate more, then you can give them their edge a greater weight, and maybe MPI will try to arrange the ranks such that they're physically closer. So that would optimize your overall thing. Yeah. So there's also a way to do this graph creation in a distributed way. So previously we were doing it a centralized way where you pass in the entire index array, an index and edges array. And so this distributed version is just that rather than passing in the entire array, you just pass in your own in degree and out degree and like source and destination vertices. So this is for my vertex, pass in the in degree, how many sources there are and the weights of those sources. And similar for the out degree, how many destinations there are and the weights for those destination edges. Then this is just extra stuff like info, reorder, and the communicator that I'm going to get out. Yeah, and then this is creating one vertex, but everybody would call this. So then at the end, you would get an entire graph topology, but this is just describing your local vertex. Example of how you'd use it. So here, process 0 has no in degree, the root. So the sources are 0, and the app degree is 2, and the destinations are 1 and 2. And for the weights, you can pass in like MPI unweighted, which is a defined thing in MPI. And then for process 1, the in degree is 1, which is 0 is pointing to it, so the source is 0. And then for out degree is 2, 3 and 4, so 3 and 4.
So if you pull this from all the vertices, would you need a barrier afterwards? Or would they all need to call it before you use any of the graph?
Yes. I don't think you need to directly implement a barrier. Like, for example, if you think about I was thinking about like when you created the Cartesian grid, for example, you don't need to call a barrier. I think there's probably some kind of implicit synchronization happening. It's kind of I don't think I also don't think that like well actually because like some of them like you could call this graph create on some of the vertices like the collectives you can also call on some of the ranks. You don't have to use necessarily all of the ranks. So similarly, I think you could create like a subgraph of the based on like the total number of ranks you have. But all the things that are participating in the graph creation cannot proceed until the entire graph has been created. Oh yeah, this is just a more generalized version of this, which is that you don't necessarily need to just have one vertex per node. You could have multiple, and just.
Is there a way you can do a barrier that only some processes need to hit?
Oh yeah, please go ahead. Are you going to answer his question?
Kind of everybody doesn't call them.
But can't you call like in collectives, for example, you can pass in like com self. Like everybody has to call the collective, but some can sit out of the actual participation. Yeah.
It's like com world, everyone.
Yeah, that's true. Uh-huh.
I'm not entirely sure.
I see. Yeah. Like but if suppose like in the beginning you had split them in half, or like the ranks, and then one of the communicators could call this one on like the first half, for example. Then the second half doesn't necessarily need to do it, and that would still be valid, I think.
Yeah, but within that half, they don't have.
I see. Yes. Yeah. Yeah, I know there are some collectives where at least you can pass in like com self or com null. Like one rank or multiple ranks can pass it in, and then like the overall communicator, but not all of them, I think. But there is definitely like this null functionality that you can pass in to some.
And if you did do that, then you would have.
Yeah. Mm-hmm. The question was, is there a barrier that you can just call on some of the vertices? I'm not sure actually. Let me look into that because I know the base MPI barrier doesn't take any arguments, so that would just be everybody. But maybe there's a way to pass in like a communicator, and then everybody in the communicator has to stop with the barrier. Probably. Yeah. I'll get back to you. Yeah, so just coming back to this is just a more general way to create the graph topology, which is that you don't necessarily need to have one node per processor, you could have multiple. And then in this example, right here, n is 2. So we're going to have nodes 0 and 1 on processor 0. Degrees are 2 and 2, and the destinations are 1, 2, 3, 4. Process 1 gets 2 nodes as well, and it'll have 2 and 5. So 2 and 5. The out degrees are 2 and 0, and then the destination 2 has 5 and 6. Questions? Yeah, whether or not you actually use the MPI like graph topology functionality, those graph representations are way more general. So you probably will need to use them in your programming assignment. Anyway. Okay, so let's move on. We're going to do derived data types, which is it's not really related. It's kind of like switching. Derived data types are basically how you represent structs in MPI. So we have built-in data types, char, int, float, double, and suppose we're going to use this example. Like suppose we have this struct. It has 1 char, has a double, and it has an array of 3 chars. And we have suppose that we have an array of 10 of these things. Okay. So suppose that we wanted to send this using MPI, and why can we not just call size of A on our machine and just do size of A times the size of MPI byte? And the problem with that is that the size of A is not necessarily the same across machines. So like, for example, suppose that machine 1, you describe size of A here, and then let's just say that it added this padding. Like you have no guarantee about the struct definition in the total actual size. You just are guaranteed that it has at least as much size to hold this stuff. So suppose that system 1 made size of A 24. It has some padding bytes in the middle, and it has some padding here. And suppose that system 2 had 16. So like it just has this padding bytes here and then one more there. And so you cannot just directly send size of A because size of A is different across these things. And so MPI allows you to specify this specific type model, which is basically a list of tuples where the tuples are the type and the displacement, which is the start in bytes of where that thing is going to start. And the type has to be some built-in type like int, char, double, so on. And the displacement is just the byte offset of where it's going to start. So for example, MPI double goes to double and then starts at 0. And then an array of ints, suppose you had 3 of them, would be they're all type int and then they start 0, 4, 8. And so we're going to use this type model like just tuples of type and displacement to start. And then the struct A would become char, which starts at 0. To represent this thing, double would start at 8, and then the next 3 chars start at 16, 17, 18. And then there are a lot of functions to create MPI data types, but the most general one is MPI is like create struct, and these are all just subsets of create struct. You don't need to use all of these. And then create struct has this API. It takes in the count, which is the size. It takes in an array of block lengths, which is, let's see an example. It's like the length of the thing in terms of, I think it's like the length in terms of actual items, an array of displacements, an array of types. Yeah, so this is like how long these arrays are going to be. How many displacements, how many types, and then you get out a new MPI data type. Usually, like there's a classic MPI thing, you pass in a pointer and you get out the result in the pointer. So here count would be n, which is the number of items that you have in this list. You have an array of types and you have an array of displacement. This n is just how many items are there. So as an example, let's go back to the struct that we had. Count is struct A, you have char, double, and the 3 chars. The count is 3. Oh, the array of block lengths is like how many of each thing you have. So count is how many distinct things there are. Like here, there's 3 char, double, and then char array. So that's why count is 3. And then array of block length, if you add them up, is the actual thing. So like this is 3 because you have 3 in this char array. And then you pass in the array of types, which is MPI char, MPI double, and MPI char, and then displacements 0, 8, 16 to get that arrangement that we just showed in the picture. Okay, and suppose that we wanted to make, oh yes. Yes, sure. Displacements are the start in bytes of where that element is starting. So usually you would start at 0. So like the types, these two arrays, like array of types and array of displacements, should match up in length because this type is going to start at this position. And then this type is going to start at this position in bytes. And then this type is going to start at this position. But this block length tells you how many of each type there are going to be. So that's why it's 1, 1, 3, because this last thing is an array of like 3.
Doesn't that make it system specific? And then does this represent the parity for each?
It's a good question. We're going to, in reality, ideally, this displacement you would like to call like pointer offset. So it's not, we're going to get to it in a little bit, but ideally you don't pass in like the hard-coded like 8, for example, for double length. You pass in like this minus start, like the pointer minus start, and that would give you the actual length that you got. Yeah. Good question. Yes, but does that answer the question about displacement? Okay. So that is how you represent one thing, and suppose that we wanted to get an entire array of these things, and we have this char. Yeah, so displacement is 0, displacement is 8, 16, 17, 18. One way to do it is like, well, we have an extra byte here, so we could just start C, and then this is exactly the same again, copied over. Actually, probably what is happening is like, because this is not ideal because you want things to start on like byte alignment, or start on like 4-byte alignment or 8-byte alignment. Ideally, cache line alignment, something like that. But this is probably not the best to have like one thing hanging over. So better is to start like later. And the way you can do that is MPI in the displacements. In addition to the types like char, double, int, and so on, it also has these special names like lower bound and upper bound, which tells you where is the struct starting and where is the struct ending. So here, the lower bound would be 0, and the upper bound would be 24. And then that tells you, that fully specifies how you do like the array of these things. Okay, so you have already brought this up, but in this code, like, it's just the same as we had. The block lengths are 1, 1, 3, the types are char, double, char, and then the displacements are 0, 8, 16. And then, yeah, so this is how you call create struct. There are 3 distinct types of items. The block lengths are given by here, the types, displacements, and then we get out the type. And then this one, they didn't use upper bound and lower bound. They called create resize, which is, which tells you just like, this is upper bound, this is lower bound, this is upper bound. Yeah, so what is wrong with this? Well, as you said, like this is not going to work necessarily in general because we hard coded in the sizes. And also we hard coded in 24 there. Okay. So to correctly determine the displacements, MPI provides this get address function where, so this is kind of like I was saying, you use the address calculations to determine the displacements. So you get address. So this is like, these are just holding them like base C, D, and E because we have C, D, and E. So get address. So we have a type A, which is the entire struct. Get the address of A, which is the start. Get the address of A.C, A.D, A.D start. which we're going to put in into C, D, E, and then now we can do address calculation on those, and that gives us the displacements. And every MPI function is going to call this, so now it's portable across different machines because we didn't just like type in directly like the number for it. Yeah, and then yeah, this so create struct is the same as before, but now we calculated the displacements based on the address calculation rather than what we think the bytes are going to be, and we pass in the type of this thing that we defined here, create struct, this MPI temp type. Yeah, we're going to get this type out here, and we create this resized, and then rather than previously this was 24, now we pass in extend, which is the size of A. And then you have to call like type commit. But that's just a thing at the end. Yes?
How would it send it between different processes if they're like got different packing or alignment on different processes? Then it would need to like move things around before or after sending it. It's just something that's bytes.
Oh, I see. Like this is fixed for a given processor. So for example, like these are actually going to show up to be constants. But this is just to make the code portable across the processors.
No, that makes sense. But if you've got an A on one processor and you want to send it to a different processor,
It's going to be the form of the A on the source processor.
but then how would you read it on the destination processor?
You read it according to the displacements.
Oh, okay. So then you just like manually copy each element into A on the destination processor.
Do you need to manually copy them? Like you can still access them according to like this A.C and so on.
I don't think you would be able to. How would you be able to on the destination processor? Just like man copy the thing you receive to an A on your destination processor.
Oh, I see. Like it doesn't line up with what it got. Yeah. Yeah, I guess so.
There's quite a lot of overhead there.
Yes. Sorry. Are these answering the question, or are these other questions? Oh yes, please. Thank you.
Okay, so I'm going to carry these. With this information. Put it over. But in practice, actually, they no longer support heterogeneous.
Oh, okay. Maybe because of this complication. I see. So you mean like there was a buffer, and then they do the copying for you?
Yeah, they pack it,
Uh-huh.
and they also include like the alignment information of the source. It no longer works.
Okay, I see. So, is there?
Saying that even if we had two processors, the alignment and packing for both of them would be the same always, right? Because they're on the same machine.
Not necessarily. Like in general, if every rank is a different machine.
But they still have to have the same packing protocol, right? Otherwise, it won't work. They still need to have the same address translation or whatever.
Like you mean this get address thing?
Yeah,
like theoretically, across machines, this get address could give you something different based on like int is maybe like a different size on different machines, for example.
but then it won't work, right?
Yeah, maybe this is why they discontinued it. Yeah.
It doesn't have a lot of overhead.
Mhm. I see. Yeah, because if they are different, like then you have to do this thing as a copying, probably. Yeah. Maybe the answer is if they are truly different, you're right that you cannot just, of course, like use the displacements directly. Maybe, yeah, like it's complicated and maybe you have to do some copying, but maybe MPI takes care of it for you in an older version or depending on the version. Yes. Cool. Oh yeah, this is just about how you actually do the padding. So so far like we did data types to represent structs. However, like sending this might be slow, one because there's this much padding, and I guess this is what you were saying before, that like MPI can create its own internal buffers to pack the data, which is complicated as well. So yeah, you can add your own explicit padding. So here, like this is the type we had. You can reorder the things in your struct. This is just outside. This is not really to do with MPI. This is just like general struct padding. So here, like you could put the double first, and then you put C and E together. So then this takes up 4 bytes, and then this padding is probably because you want the whole thing to be cache line aligned. Create the data types. We did MPI create struct, and then there are a couple of other useful ones. One is MPI type contiguous, and one is MPI type vector, and I will show some examples. So MPI type contiguous here, like suppose you had a pair x and y, and then contiguous, you would pass in how many things there are, the type, and then like this is kind of just giving you like an array of those things. And then for MPI type vector, it kind of like allows you to extract out non-contiguous data. So suppose that we have this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and in row major order you would just put the rows one after another 1, 2, 3, 4, 5, 6, 7, 8, 9. And suppose that we only wanted to send one column, or like arbitrary columns, and we want 2, 5, and 8, but of course those are not next to each other. And if we wanted to, and if we want to do like send or scattered, the data needs to be contiguous, so it's not going to directly work. And then this is an example of how you would use type vector. So let's say we have the matrix that we just had in row major order, and we're going to create a column type to describe the column. Type vector has 3, 1, 3. Type int and column type. Oh yeah, let's go back to the API. So count, block length, and stride. And then this is the old type, and then this is the new type. So count is how many of these ints there are going to be, so 3. And then block length is 1, which is how many things you're going to take contiguously. And then stride is 3, which is how many you're going to jump. The type is int, and then you put them into column type. And you're going to commit column type because you commit MPI types. This is our 3 by 3 matrix. 0 up to 8. And to send the column, you would pass in the buffer, one of the column type in the receiver. And this is 0, 1 because we're sending the first column. So we had 3 things that were going to be in the 3 ints that are going to be in the column. We take 1, and then the displacement is 3 to loop around. And then you just receive it, and that's it. Oh yeah, there's another thing, create resized. So this is like, so the previous example, we were sending one column. Suppose that we want to scatter the columns, but we have the thing in row major. This example, column resized. This is the initial type, column not resized. Let's go back to the API. Wait. Column not resized is weird. Oh, okay, I see. So initially, we define a vector. This is the initial column, which is how many cells you have in each column. And then 1, I think, which is the block length. And okay, I see. This is just like you just change the indexing because in scatter you pass in column resize as your type. And then you pass in the cells per column, or you pass in a vector of my column, which is here. that one is probably less common, but the structs at least like it is good to define the structs in MPI type rather than in type, yes.
How that also works is
Yeah.
like what's the since the resizing zero size of it, but somehow that gets the whole matrix.
Sorry. Okay, so yeah, so we start with the original column not resized. You define a vector, which is length plus per column. And then that is defined as column not resized. And then to this create resize is just ensuring that you do sorry, I'm trying to remember the API of how this works. Hold on. Okay, yeah. So this is okay. So this is type create resize, and then it takes in some old data types, the lower bound, the extent, which is the length, and then yes, okay, and then yeah. So old data type is the size that you're going to resize. So previously it was column. Lower bound is the new lower bound you're going to give it, and then extent, which is the upper bound that you're going to give it. And so this is the example, similar to the example that we were just doing. You're trying to send the columns, but it's in row major. And then if we look at this, so here, therefore, cells per column, but it doesn't really matter. And then this is the same example that we were just doing, which is we start with a vector data type here, and then we have create resize, which is the initial type, the start, or like the lower bound, the extent, and then the column resized. Okay. So to get out the column, we need to do this thing, which is we take out the first element. Like it's in row major, and we're trying to take out like the first element in. This is just the first column in each. So we would take the first element in each row. So this is like the length that we're taking, which is 1, and then this stride needs to be 3, and that is already defined. When we define that, when we define the column type, which is here, this thing. So it's like cells per column is how many we would extract, and then cells per row is like the displacement goes around, and then this thing is the block length, which is 1. And then oh, I see. You just have to do the reason for this resizing is because if you're trying to do multiple of them, like the thing that we just did is going to work for one column. You just pass in the offset, but it doesn't work if you're trying to do multiple columns because, like, if you just start because the data is interleaved, and usually with the data types they ask them to be contiguous. So this is just like it's sort of just like a general functionality thing. There's nothing really like fundamental about it.
more columns than rows, then this won't work. So it starts overwriting the last, because if it just puts them, I think in this case, the person starting at 0 is going to like, I don't know, it kind of recreates the same layout as the original row feature vector. Oh, no, never mind.
No, it doesn't work for arbitrary rows and columns. I have like a few minutes left, so really quickly, you can also define custom operators MPI. So we had, for example, MPI sum, MPI max, and so on, and you can define like custom operators. So for example, let's say that we wanted to do this function, which is you have tuples a, I, or like yeah, you have these tuples, which is like a and b, where these are your two things, and then you want to implement like a specified operator. And yeah, we already have these, reduce, scan, and so on, and you have to pass in an operator to those, and we already have these things. Most of the time you just use these like sum and product are the main ones. But yeah, this is how you pass in, this is how you make an operator. So you pass in a vector, in vector, and out vector, and then, oh yeah, and then you overwrite, I guess, in out. So this is your operator, and then length is the number of things that you have of set data type in here. And then, yeah, you have in and out, and then you just specify the operator. That's it. That was really fast. But that's it. Cool. Yeah, so in terms of the programming assignment, so basically the way it works is that you get, like I said, you get a list of tuples for a sparse matrix, and you have to do some kind of operations on it. And often in algorithms, it may be more convenient or faster to convert the initial list of tuples you got into a more optimized format, such as compressed sparse row. So yeah, so that is something that you can do here. Like you just iterate over the list of tuples. And for sending, I guess you just mostly need to send tuples. So maybe you don't really need such complicated data types, but you could also define, like, of course, tuples using the functionality that we had today. Yeah. Yeah, in the homework, I think the most initial, like the easiest thing to do initially, and probably all you need to do is, we talked about a lot of partitioning strategies for dense matrix algebra, like 2D, 2.5D, and so on. We are doing sparse matrix multiplication, so probably 1D is sufficient for this assignment. You just partition the rows in a blockwise way. Cool. Yeah, take a look at the homework, or take a look at the programming assignment, and let me know if you have any questions.